Our next speaker is Attia from Massachusetts Institute of Technology. He's studying chemical engineering, and he conducted his practicum at Lawrence Berkeley National Lab. So let's welcome Lucas.
Awesome. Thank you, Jeff, for the introduction. It's great to be here. It's crazy to be wrapping up my last program review, but happy to share this project with you all. So this was a project that started about a year ago, and it's kind of a small part of my thesis, but I really want to share I want to start off by sharing a bit about how this project came to be, and just as an encouragement for you all to really take advantage of the flexibility that the CSGF offers. So this project started out as an idea that I had along with Jackson, who's a third-year fellow, and we actually both took a course together at MIT called Machine Learning for Molecular Engineering. And we were really able to nurture this idea in this course and bring it into be a paper and a project that has follow-up work and collaborations with industry. So just as an encouragement to you all to really maximize the CSGF while you're still on fellowship, and any crazy idea you have, just go for it. So yeah, but this project is all about solubility and predicting solubility. So just as a little bit of background, thermodynamic solubility is a fundamental solution property. So this describes the thermodynamic equilibrium between two processes. So dissolution is represented by the red arrows, which is a solid molecule dissolving or solubilizing into solution. And that process is in equilibrium with crystallization or precipitation, where a solubilized molecule crashes out of solution and solidifies. So that equilibrium concentration is referred to as solubility. And this is a really important process for the property for the chemical sciences, and particularly for synthetic and process chemistry. It's really crucial. So in process design, imagining chemical synthesis processes and crystallization, it's kind of obvious why this property is really important. Thinking about applications in drug discovery and drug development, the way you formulate and deliver drugs also really depends on this property of solubility. And in environmental chemistry as well, the way we think about environmental impact and toxicology is also related to solubility. So for that reason, this property is extremely important and has been of interest to the chemical sciences for a long time. And in the context of drug discovery and kind of industrial workflows, experimentally screening solubility or determining solubility is extremely resource intensive. So it can take up to milligrams or even grams sometimes of some molecule to screen, and it can take days to find a hit. And this is really a rate-limiting step in a lot of discovery pipelines. So for this reason, the resource burden of this experimental determination really has motivated a lot of a priori prediction work. So where has the field turned to predict solubility a priori from structure alone? May have gotten cut off over there, but that says historical methods. So historically, we've really looked at these types of group additivity and quantum methods. So Cosmo is a very popular method that is used in industry, but these approaches are really limited in their accuracy and have kind of motivated people turning to ML recently. And some of the early work using ML for solubility prediction really lacks generalizability. So this was kind of a landmark paper about 5 years ago, but really only worked for 2 to 3 different solvents of interest. And the state-of-the-art work is this paper from Vermeer, which I'm going to kind of reference a few times throughout the talk, because this is kind of the benchmark that we'll compare our models against. And this model is actually kind of 4 models ensembled together. They each predict different solution properties, so an enthalpy, a free energy, and an entropy property, which are combined in a thermodynamic cycle to then predict actual solubility. But this model also has limitations, which I'll share a bit more about later, that have kind of limited its use in real workflows. So our goal is really to develop an accurate and general model to predict organic solubility. So we use 2 different approaches to represent molecules for machine learning. So one approach actually is using a model that Jackson developed, which is a descriptor-like approach. So in this kind of approach, you calculate different features that encode information about your atoms. This is a very classical, about your molecule. This is a very classical approach. So information like the atom types, topological information, the charge distribution, can all be calculated from the structure alone. So a 2D representation or a string representation of your molecule can give you this type of information using different calculators. And those features are then put into an embedding, which you can feed into a neural network. And the specific model we're using for this approach is called FastProp. The other approach we're using is kind of been, I think we heard a bit about this from Bowen in the morning, but graph-based models, where we actually do some sort of graph learning, whether it's message passing or graph convolutions on the 2D connectivity graph of the molecule. So in this case, we actually learn a molecular embedding rather than have a fixed embedding based on molecular descriptors. So in this case, we have this learned embedding, which then similarly we can pass into a neural network to predict some property of interest. So in this case, we're using ChemProp to accomplish our graph-based representation. So our approach here is actually quite a simple approach that we use. So we end up taking our mapping, whether it's through a fixed descriptor approach like FastProp or a learned representation approach like ChemProp. We concatenate our representations to get this representation of our solution, which then is regressed to solubility, which is represented by log S. This is the log of the solubility. And yeah, so thinking about the data that we use in our models, just looking at what one solubility experiment might look like. So you have, for a given solute and a given solvent, you have different measurements at over a range of temperatures. And you have this kind of monotonic behavior with temperature, which is pretty classical for solubility. You have an increase as you increase the temperature. And there's a lot of data sets in the literature that have been compiled from thousands of different experiments and published papers with this type of data. So we use two specifically. One is called Big Sol, which we use to train our models, and we test on another one, SolProp, which came from that Vermeer paper, which is our benchmark model that we're going to compare against. And one kind of interesting feature that I'll come back to in a little bit about these compiled data sets is actually measurements can vary by up to an order of magnitude between labs, which obviously poses a problem for machine learning, which I'll come back to later. So in this case, this is showing a specific solution that was present in both data sets, and we can see that the measurements are off by over an order of magnitude, actually. And this is something that's kind of known in the literature, and if anyone's curious about why this is the case, I can share a bit more. But yeah, this is going to be something that we'll come back to in a little bit. So I won't share too much about the training details, but one interesting thing we did with our model training that I want to highlight is gradient-based regularization. And this is kind of a very general approach that anyone who's doing anything in machine learning can easily implement if it makes sense. So in our case, this is showing the gradients of solubility with respect to temperature. So this plot here is a cumulative distribution of the solubility gradient with respect to temperature in the testing data set. And if we train a model with a traditional loss function where we only penalize predictions on the solubility itself, we see this learned distribution of gradients has some systematic bias compared to the baseline ground truth distribution of gradients. And if we actually include just a very simple gradient-based regularization term which penalizes directly the gradient predictions inside the loss function, where you only need to have one parameter that rescales your magnitude of your penalties to be the same as the magnitude of your penalties on the solubility predictions themselves, we can actually learn a really accurate gradient prediction distribution. So you can imagine this is an extremely general approach that you can use for any type of machine learning model where you care about the gradients of your targets with some input variable. And this approach was actually published at NeurIPS a few years ago, but it's kind of died down. But we're excited to kind of bring this back and revive this and hope that we can find, others can find uses of this type of training trick in their applications. All right, so looking at the actual performance of our model. So I mentioned this benchmark model. This shows a parity plot of the solubility values on that testing set. We have an RMSE of around 1.4. Again, this is in log space, so this is saying that we can only get accurate predictions well over an order of magnitude. And we have about 67% of predictions are within that metric of one log unit. And then for our two models that we developed, both the ChemProp and FastProp, the learned and the fixed descriptor representations, we actually have extremely similar performance. So we've reduced that error down to 0.8, so almost cut the error in half. And we've increased the percentage of predictions that are within that plus or minus 1 log unit kind of range. And just to look at a couple of case studies of specific solutions. So this one is looking at risperidone, which is an antipsychotic drug used to treat schizophrenia. Thank you. And this is looking at the predictions in 2 different solutions. So we have acetone and isopropanol. And the points show the experimental values. The dotted lines are the benchmark model, and the solid lines are our model predictions. So for this example, we can see off the bat our model predictions are a lot more accurate. We also can see that our uncertainty in our model predictions has decreased a lot. And we get that uncertainty from ensembling a few different models predictions as well. Another example is this one, which I think is really interesting. This is L-preliminide, which is an amino acid derivative. This is used as a catalyst. It's also used as a precursor for peptide synthesis. So in this case, we're looking at the solubility in hexane and heptane, which are extremely similar solvents. So they differ only by a single carbon. And actually, the benchmark model can't differentiate between these 2 solvents. So it predicts the same solubility exactly for these 2 different solvents, whereas our model is able to actually differentiate between these extremely similar solvents and actually gets the ordering correct of heptane being, the molecule being more soluble in heptane than hexane. So this is a really encouraging case study for us to show that we've really learned a good representation, particularly in our learned representation model. So going back to this idea of experimental variability in our data set. So this plot here is showing how our testing error changes as a function of the size of our training data set. So as we change the number of points that are available to the model to learn from, we can see this kind of plateau in performance that caps out around an RMC of 0.8. And we actually went back and calculated the experimental variability in our testing data set. So between labs for the same solutions, what actually is that variability? And it actually comes out to be just below our performance. So for this reason, we're pretty confident that we're actually approaching that experimental kind of accuracy limit, which tells us that our models are doing about as well as they can with the data that's available. And this is kind of one of the main results from our work is actually kind of a call to action for the field to really encourage a single lab to produce a large data set rather than the kind of what people are doing now, which is just compiling data sets across the literature. This will kind of unlock more accurate models if we really can have a single lab produce a large data set. And this is something that in other molecular property prediction fields has been something that people have called for, but really emphasizing that in solubility, this is going to be kind of the rate limiting step at this point. So what we're doing now actually is extending this towards a causal framework. So this is something that we're really excited about, and this is in collaboration with Neopoly, which is an AI for science company. And they have expertise in causal machine learning. So rather than mapping our representation to solubility using a neural network, we're actually using now a causal regressor, which gives us structural information. It also allows us to do interventions and counterfactual predictions on our molecules. This is really exciting for molecular design, and this is kind of something that we hope to get out by the end of the year. So a few takeaways. The CSGF lets you be flexible, so take advantage of the fellowship while you're on it. I've had an absolute blast just being able to pursue different areas, and this project was something that came up, and the CSGF allowed me to pursue it. This project was really all about producing a general and accurate solubility model, which we demonstrated we were able to make. I also emphasized gradient-based regularization and how this trains our neural networks to capture temperature dependence. And I encourage you all to try Sibyl training with your neural networks as well. I also emphasized how our model accuracy is approaching the limit of experimental accuracy, and any further gains we believe really need to come from improvements in the data itself. So with that, I'd like to acknowledge my PI, Pat, who really has been an awesome mentor throughout my PhD, as well as Jackson and Bill's group, who were collaborators on this project. And also SuperCloud. I didn't mention our kind of high performance part of this project, but we definitely exploited SuperCloud at MIT for lots of hyperparameter optimization runs. So thanks to them and to Berkeley and my practical mentor, Sam, who also was just a really great mentor and really got me interested in machine learning a couple years ago. And with that, I'd like to thank you all for your attention and happy to take any questions.